first place, thank you very much for Piyali and the other people in Bangalore for organizing the Pencil Code user meeting this year. It's been very nice to be able to join and to present my work. So I will be working about some recent work in order to compute the gravitational wave signal, as the title says, produced from primordial magnetic fields. I will not talk very much about the actual results and comparison with pulsar timing arrays. They are in the end of the slides, but I will try to focus a bit more on the results from the numerical simulations and the new results that we have obtained with the objective to analyze pulsar timing array, which I will be explaining in a moment. So I would also like to thank some of my collaborators in these works, which are some people at APC and also some people like in the Pencil Code community, like Axel and some other people. So I will be showing the results from mostly from these two papers. So again, if then you want to see more about the results and everything, please, you can just ask me anything. We can discuss on Slack, or you can just go into the archive papers. So in first place, I think it's kind of mandatory for also, by the way, tomorrow we will be having a discussion. So I'm also using this talk in order to give some introduction for people that are outside of the field in gravitational waves. So we'll be having a discussion on different topics that have been studied within the Pencil Code meeting. So I hope that this is also a way to introduce in gravitational waves for people that are not actively working on it, so they'll be able to join tomorrow's discussion and follow it this year if they are interested in that. So as you might know, the first detections of gravitational waves occurred back in 2015, and they were observations of a collision of two black holes. And they were observed for the first time by Hanford and Livingstone by LIGO in the US. And since then, we have had many different observations of compact binary objects, events producing gravitational waves. So a very important observation was in 2017, when there was the first observation of a neutron star binary merger. And also the first observation of not only the gravitational wave signal, but also its electromagnetic counterpart, which allowed us to understand much more about neutron stars and these processes. For example, also it allowed to put the first constraint on the speed of propagation of gravitational waves, as well as the first observation from gravitational waves of the measure of the Hubble rate at present time. So since then, there have been several events. At the moment, the LIGO, also in collaboration with European Virgo, and now it's joining the Japanese Kagre, and also in the observations. They will be starting the fourth run of data at the end of the year. This has been slightly postponed due to the pandemic, as many other things. And at the moment, there is a total of 90 events which are made public through the observations, the O3b run of observations. But in any case, this is regarding astrophysical generation of gravitational waves, and I actually will be focusing, and it's also what has been mostly done within the Pencil Code community, in cosmological sources of gravitational waves. So we expect that several processes during the very early universe will be producing a cosmological background of gravitational waves that will be happening in the universe as a whole. And since they are very far away from us back in time, they are not able to be resolved individually like these previous events from astrophysical sources. So what we expect to observe is a stochastic superposition of different gravitational wave signals that we can characterize them through its spectrum and then the radiation in frequencies. So some of these sources in the early universe are, for example, phase transitions. So there are some epochs in the universe where the universe goes from one state into a new state that are happening much earlier than recombination, which is when we have our first observations of electromagnetic radiation, for example. So therefore, with potentially we can go to much earlier times than that with the observation of gravitational waves. So I will be mostly focusing on the quantum chromodynamic phase transition. So when the quarks when the temperature of the universe is such that the quarks start becoming confined, which occurs at around 10⁻⁶ seconds after the Big Bang at the temperature scale of around 100 megaelectron volts. And this is relevant for observations by pulsar timing array that I will be showing in a moment, since the range of frequencies for observations is around nanohertz, from 1 to 100 nanohertz, more or less. So this is where we expect the signal coming from the QCD phase transition to be peaking around. Also, if we consider the electroweak phase transition, so when the electroweak symmetry is broken into electromagnetism and the weak force, then this could be, which happens at around the temperature scale of 100 gigaelectron volts, so earlier in the history of the universe, or around 10 to minus 11 seconds. This would be peaking at around frequencies between 10 to minus 5 and the millihertz, which is also the peak sensitivity of space-based gravitational wave detectors, as the planned mission LISA. And if these are temperature scales that more or less we know what should be happening from collider physics and other experiments. But if we go to even earlier times in the history of universe, or to even larger temperature scales, we might also have more exotic phase transitions that would be happening, for example, around 10 to the 7, 10 to the 8 gigaelectron volts, which are more unknown and not as clear what is going on at these temperature scales. So this is more untested physics and some extensions of standard model. But if we have such phase transitions, this would potentially be probed by future generation of ground-based detectors, as the Einstein telescope or Cosmic Explorer, which are expected to have much better sensitivities than the current LIGO, Virgo, Kagra constellations. So also, besides phase transitions, we might also have signals from inflation, as, for example, Axel was presenting yesterday, some recent results on inflationary magnetogenesis. So you can see his presentation, also some work that he has been doing with Ran Kishore and Yu Tonghe and other people, but they are here in the Pencil Code user meeting. So I will be mostly targeting this generation of gravitational waves at the QCD phase transition, since this is it's going back all the time, since this is actually what can be potentially observed by pulsar timing array, which I will be showing in a moment. So we know that if there are signals produced at these epochs during the early universe, we might have different ways to detect these gravitational waves. But what is actually sourcing that? And the source that I will be now focusing, and we're mostly interested in, is magnetohydrodynamic turbulence. And that's also the interesting source regarding why we're doing simulations using the Pencil Code. So we might have different processes that can lead to the generation of primordial magnetic fields, for example, or to the generation of hydrodynamic turbulence. For example, if we have some extensions of the standard model which lead to first-order phase transitions, either the electroweak phase transition or the QCD phase transition, we might have also very violent processes during these phase transitions that will lead to the development of hydrodynamic turbulence. So these are two sources, and actually, if we have any of these two, we expect them to be highly coupled due to the very high conductivity of the universe, and we also expect these to develop MHD turbulence. Besides MHD turbulence, we might also have different sources during these phase transitions, as, for example, actual collisions of the bubbles that are produced during the phase transitions. So I'm not going into much detail, but we might also have sound waves, even if we don't have the presence of turbulence. We can also have cosmic topological defects, for example, cosmic strings, and primordial black holes. And in the end, we expect that the cosmological gravitational wave background will be a superposition of many different sources. So it's extremely important to actually understand what are the contributions of these different sources, and therefore to understand what is the contribution from MHD turbulence in these cosmological gravitational wave backgrounds, such that once that we have this type of observations, we're able to disentangle what are the contributions from different sources, if all of them are present or if only some of them are present. And therefore, in order to understand what are the processes that are leading to the generation of such gravitational waves. So I will be focusing here on primordial magnetic fields. And so, for example, we can either have a magnetic field that is produced during the phase or is already present, and that leads to generation of gravitational wave signal. That is what I will be showing then the numerical results about this. So as I was saying, there is the primordial plasma, and then this will to MHD turbulence. One way of, for example, we have a present magnetic fields that can be actually reinforced by turbulence or actually created directly via MO. So these are different ways that we expect to have a magnetic field either present or produced. And I won't go into what are the different mechanisms leading to the generation of magnetic fields, but there are different proposals. But we expect them to be produced during the early universe, for example, from some observations at present time. Because if we have a magnetic field that is produced during the early universe, that magnetic field will evolve through the history of the universe, and we should be able to, and it should be present at present time, the relics of such a magnetic field in the very large scales of our universe, for example, in cosmic voids. So there have been some observations by the Fermi collaboration that put some lower limits on what are the strength of such magnetic fields in these very large scales magnetic fields. Oops, sorry, for some reason it's going back and forth. So on the other hand, we also have some maximum amplitude that we can consider for the strength of these magnetic fields, because otherwise it could be ruling out the Big Bang nucleosynthesis. So we have some lower limits and some upper limits of what we expect these primordial magnetic fields to have its strength in the early universe. So therefore, we can consider that there is some primordial magnetic fields present. For example, in this talk, I will be focusing on if it's also applicable to the electron phase transition, and therefore study what is the actual production of gravitational waves, and due to the presence of such primordial magnetic fields, and due to the production of MHD turbulence. So let me go very quickly again over the gravitational wave spectrum that we're expecting. So as I was explaining, in the very large frequencies, we have the observations by ground-based detectors. So this is the sensitivity of Hanford-Livingstone in the O2 runs, and then with the expected sensitivity with the joining of CAGRA, as well as the sensitivity of future ground-based detectors like Einstein Telescope, Cosmic Explorer, which are expected to be around in the late 2030s. And then if we go into space-based detectors, like for example, LISA, then we go into the millihertz range, as I was explaining. There are also other experiments and also future generation of space-based detectors that are planning to cover the intermediate frequencies. And now I will talk about pulsar timing array. If we want to go into smaller frequencies, then we can use pulsar timing arrays. So there are different that have been collecting data, so they use an array of to observe the delays of the arrival time of these pulses of measures that are coherent for different pulses. So if you have an array of pulses, you can then correlate these time delays and actually try to induce presence of gravitational wave background. So this has been done by several collaborations, and they are joined in the international collaboration. And interestingly, in 2020, the Nanograph, the American collaboration, after 12.5 years, using 12.5 years of observations, they reported a common process spectrum over several pulses. That this is the observed common process delay times, and so as a function of frequency, and these are the data points, and they were able to feed a power law into these data points that at the moment are very few, but at least this is common over several pulses. So this is a very promising observation. The only problem is that according to general relativity, if we study the correlation among pulses as a function of their angular separation, this is expected to follow what is called the Hellingsdown curve, which corresponds to quadrupole. Is the blue line here, and these are the observations from their data sets. So therefore, it is not statistically significant that this is actually following a Hellingsdown and not a monopole. There is not a strong significance for that. So at the moment, we have some common process that might be due to gravitational waves, but until these collaborations are able to collect enough data and to show with enough statistical significance that it is following the Hellingsdown curve, we cannot claim that this is a gravitational wave background. And definitely, we can still not claim that. spectrum over pulses, and in the next coming years, this might be confirmed to be due to a presence of a gravitational wave background. So the collaborations, I skip this quickly, but the Parkes pulsar timing array collaboration, which is Australian collaboration, the European, and then the international collaboration, they have reported similar results. So like a common process spectrum, which can be fitted into a power law, although they're with kind of statistical significance to claim this follows the Helmholtz curve, which is required to claim that this is a gravitational wave. The results of the different collaborations in the nanohertz, and these are the power law fits over the range of frequencies that they have been observing. And if now we consider the different signals coming from phase transitions are produced by MHD turbulence, they would have such a characteristic spectrum. And this is now using an analytical model that we have developed in this paper. And for this analytical model, we have been using simulations from the pencil code in order to validate this model and also to give some semi-empirical parameters that are necessary to reproduce this model. So in this paper, we performed these MHD simulations that I will be now presenting them and some of the numerical results. And we developed the analytical model, and then we can apply it to different generation temperature scales. For example, we apply it at the QCD temperature scale, then we have something that is completely compatible with the observations by pulsar timing array. If we have a process at the electrowave phase transition, we see that this could be detectable by LISA. And if we go into more exotic phase transitions at very large temperature scales, then we might have something that in future will be potentially detectable by Einstein telescope or Cosmic Explorer, or general any 3G ground-based detectors. So in order to compute the signals, we have been using the pencil codes. We have solved for radiation-dominated era, and this I have been talking also in previous pencil code user meetings, and also Axel has been talking about this. So I will, the next few slides, which are more into the equations that we're solving, I will try to skip that to go into the numerical results. But again, like if you have any questions, so you can ask me. We can discuss that on Slack, and also I'll put the PDF, the PDF of the slides so that you can check those at any moment. And we have so we started working on this in 2017 with Axel during my PhD. So we implemented the gradation module back then, and since then there has been many different studies regarding gravitational waves. So this is also what we will be discussing tomorrow, an overview of not several awards that have been in gravitational waves. So yeah, so as I was saying, I will see this quite quickly so I can go into the numerical results. But what we're doing is we have different contributions into the stress energy tensor coming from fluid motions and coming from the electromagnetic fields in covariant formulation. So we have also viscous stresses. And if then we want to compute the conservation laws, then we derive the usual MHD equations with some additional terms that are appearing due to the use of a relativistic equation of state for the pressure, which is which corresponds to modeling the early universe at the so we have also on terms on the equation, and we can either model these equations without any forcing if we have some forcing functions either for velocity fields or for magnetic fields if we're interested in modeling some things that are not covered by MHD, and actually we need to velocity magnetics. We can use this here. So just as a quick comment, and also connect this with the work by other people, by Jennifer Schober, by Matthias and Newton. They have been studying also the chiromagnetic effect, and also in the context of generation of gravitational waves. And in the case where if you have a chiromagnetic effect, then you might have an additional current density that is produced by the presence of a chemical potential, which is due to the difference between left and right-handed particles. So I don't know why I'm not touching anything and it skips slides. I'm sorry about that. And for this, and I think there is a talk tomorrow by Jennifer, so probably she'll be talking about this in much more detail. This is pretty interesting work that they have been doing also. So regarding the gravitational wave equation, so what we're solving is the linearized Einstein field equations, where we assume a homogeneous and isotropic universe and some tensor mode perturbations over the metric tensor given by the Freeman-Lemaitre-Robertson-Walker model. And we derive the gravitational wave equation, where we have the strains wave equation and the source and the linear source due to the stress energy tensor, which are projected into a traceless and transverse tensor. And this is the equation that we're actually solving at the moment in the pencil code. So again, this you can ask me any questions, but I'll kind of skip and go into the numerical results that we have been doing for this specific work. We are considering non-helical magnetic fields, although this can be extended to helical fields, but it was for our purposes, it was interesting to consider non-helical fields. And we start with an initial magnetic field that is completely that it has already developed turbulence, so that it follows a bisolar spectrum in the larger scales proportional to k to the fourth power, and it follows a Kolmogorov spectrum in the inertial range proportional to k to minus 5/3. It is slightly modified with some pre-parameters. This is the magnetic energy density spectrum with some pre-parameters such that this EM star is actually the value at the peak, and this K star is exactly also the position of the maximum amplitude of the spectrum. And we have some smoothing parameter, which we call alpha, and we set it to be equal to 2, such that these models the transition from the Beer's law spectrum into the Kolmogorov spectrum and how smooth it is. You can find details about this type of initial conditions in some of these papers. And in order to compute these simulations, we have some parameters. So the first parameter is what is the total magnetic energy density or the strength of such primordial magnetic fields at the time of where we start our simulations. This is modeled as a fraction of the total radiation energy density at the time where these magnetic fields have been generated or where the gravitational wave signals are generated. And this is in principle limited by big nucleosynthesis to be around 10%. Although some recent works actually by Tina Kagnashvili and Axel and other people, they have reconsidered this limit to not be as stringent as 10%. So it's something that we will be considering also, like larger magnetic fields, but at the moment we'll stay to a 10%, which was initially thought to be the Big Bang nucleosynthesis limit. Then we have a spectral peak, which is normalized by the horizon scale at the time of generation. So it should be larger than 2 pi by causality, and then it can be any number, and we keep it as a free parameter. And finally, the time at which these gravitational waves are produced, given through the temperature scale. So these are the results of some of these simulations. So we start with a spectral peak that is around 15 times that of the horizon scale, and 6.5. And this is because these are the scales that allow us to compare this with the results from pulsar timing arrays. So these the characteristic spectrum, and this is something that we found initially in the first numerical simulations of this type, is that we have an inertial range that follows like k to the minus 8/3, or in frequency f to the minus 8/3. And then something proportional to k, which I was presenting this in previous pencil code user meetings, and it was our initial work with Axel. And we were expecting this to, at some point, it should go into something proportional to k cubed. So in order to find this proportionality to k cubed, I had for this work, I had to run different simulations with different domains, with very large domains, in order to go into the larger scales. And if you run these simulations for long enough, and then you take the envelope of the oscillations at every wave number, then you find that this actually follows a k to the third power, and then goes into something that is approximately proportional to k. And I will explain this in a moment. So the dots are the results from the numerical simulations, and the black lines are actually the envelope that we obtained from the analytical model that is trying to model this. And run A is for a run with a small edit turnover time of around 0.18 in normalized units with respect to the Hubble time. And runs E are 1.4, have an edit turnover time of 1.4. So they're actually much slower, slowly dynamically evolving the magnetic field in this type of simulations. And therefore, what we observe is that when we have a larger edit turnover time, then the position of this break into the K cube part of the spectrum goes into smaller wave numbers. So we initially speculated that this should be around the order of magnitude of 1 Hubble scale, and this is approximately around that. But the exact location, it depends actually on what is the edit turnover time of the magnetic field. And we have something that follows this K, proportional to K, but then it goes into a shape that is proportional to the logarithmic squared, as I will be now showing for the analytical result. So for the analytical model, we first can solve the gravitational wave equation, where Hij are the strains of the tensor mode perturbations. Then we have the stress energy tensor into its tracer and transverse projection. And we solve the gravitational wave equation down to some final time, which is a parameter that we cannot know from our analytical model, but it's modeling the effective duration of the turbulent sourcing. And therefore, the gravitational wave spectrum is computed through the unequal time correlator of the stress energy tensor coming from magnetic fields in this case. So this is pretty complicated to model from an analytical point of view. So that's why we actually need to perform these numerical simulations. But in order to develop this specific analytical model, what we observe is that the magnetic field evolution is in general much lower compared to the dynamical evolution of the gravitational wave at every mode, which is proportional to 1 divided by K. And then if you compare that to the edit turnover time, where you have the Alpen speed, due to causality, unless you go to Alpen speeds that are very close to the speed of light, then this will in general be smaller. So as a first assumption, we consider that the magnetic field evolution is very slow, and that we can consider this unequal time correlator to be approximately constant in time. And taking that approximation, we develop this analytical model, which gives the proportionality to K cube. It depends on the strength of the magnetic field, the amplitude. These are just some numerical values of order 1, actually. And this is actually some function that we can compute and depends on the spectral shape of the magnetic of the magnetic field. And I will be showing that in a moment. And this shows the different two regimes. So one is constant. This gives the K cube proportionality. It just depends on this parameter, which is the effective duration of the turbulent sourcing. And the other one is proportional to this logarithmic squared of 1 plus 1 divided by K. And this is actually the shape that we are observing here following in these simulations. It would correspond to this range. And when wave numbers are much larger than Hubble horizon or are just larger, this function can be approximated as 1 divided by K squared and then multiplied by K cube. It gives the proportionality to K that we found in earlier numerical simulations, so that we also find here when we are getting close to the peak and where we're having a very short edit turnover times. We find that this is close to this position, so therefore we only observe the proportionality to K. So yeah, I'm actually almost running out of time, so I'll just show that this spectrum that depends on the magnetic spectral shape. It has a shape that is approximately constant, so therefore it could explain, as I was saying, like the K cube and then the K cube divided by K squared regimes. And then when we go to wave numbers above the spectral peak of the magnetic field, then it develops into the Kolmogorov expected spectrum, which is K to the minus 11 thirds for the convolution of the magnetic field, which is this is how it can be computed if we assume Gaussian fields. And this is the numerical value of such an integral for the specific spectral shape that I was showing at the beginning of this smooth broken power law. And this K to the minus 11 thirds, then it's multiplied to K cube divided by K squared, so K. And this is what gives the spectrum proportional to K to the minus 8 thirds in the inertial range for the gravitational wave spectrum. So this is my final slide. So we have in this analytical model and this T final, which is the effective duration of the turbulent sourcing, that we cannot predict from the analytical model. And in order to do that, we are doing several simulations to fit a relation between the final time and the duration of the turbulent sourcing and the eddy turnover time, as we expect this to be a function of the eddy turnover time. We have only fitted these for the parameters that are actually relevant for the observations by pulsar timing arrays, but we expect to study this more in detail and to be able to actually give a better fit, such that we have like a closed solution from the analytical spectrum where we're considering that the magnetic field is initially present, which I didn't talk much about that, but that's one of the caveats of this analysis. So therefore, from the simulation, we have validated the analytical model. We are able to give a fit between this effective parameter that appears in the analytical model with the eddy turnover time of the magnetic field. And therefore, we have now all the ingredients to, for example, compare this with the observations by pulsar timing array that I was presenting at the beginning. And that, again, I don't have now time to explain this. I wanted more to go into the numerics and the development of this analytical model. But we have then developed the analytical model, and we can use this in order to constrain the parameters K star, the characteristic spectral peak of the magnetic field, as well as the amplitude of the magnetic field, with observations by pulsar timing, by the observations of pulsar timing array. So that's what we did in this work, and we were able to give some constraints for the different observations, and then finally consider these magnetic fields and how they are corresponding to different observations and different constraints that we have from primordial magnetic fields. So again, sorry I went very quickly through this last part, but you can just ask me about it and we can discuss that further. So yeah, so my final conclusions is that we have performed the numerical simulations using the pencil code in order to study the production of gravitational waves due to MHD turbulence, which important source of gravitational waves, and it's very important to understand what is the spectral shape and the different parameters that enter into play for the spectral shapes in order to, when we have observations by pulsar timing array, by LISA, to be able to disentangle the different sources and actually say if we are observing a signal produced by primordial magnetic fields or produced by primordial turbulence in the early universe. And then we develop compute what are constraints on the different parameters and not to have to run a simulation for every set of so F cube larger scales. It develops this proof, which is actually some logarithmic function, and then it goes into the inertial range. And this is all I wanted to share. So thank you very much for your attention, and yeah, thank you, and let me know if you have any questions.
Yeah, thanks, Alberto. Very elaborate talk. So let's see if we have questions. I suppose there will be more explanations. Somebody is clapping. No. So I suppose you will be able to cover this more detail during the discussion, maybe, right? Or
Yes. So I think I went a bit over time, but I also wanted to give some introductions so that tomorrow people can also follow more into the discussion.
I don't see any raised hands, but I had a naive question actually. So you mentioned that there is this electroweak symmetry breaking, and so I thought you were incorporating it in the relativistic MHD equation somehow, or so how is that being done? This electroweak symmetry. What impact does it have on the?
I lost the connection for like a second. So what is? Can you repeat the question? Sorry.
Yeah. So you mentioned that you have this electroweak symmetry breaking, or you are tackling the epoch after electroweak symmetry breaking, right? So
yes.
How do you incorporate that in the equation? I mean, it is some parameter or some